Yeah, so I adhere to the request not to thank the organizers, but let me express my gratitude that I can stay here, cure my cold, and enjoy the great Indian food for a few days. Also show you some of the results we received over the past years on, to use John Cleese's words, a completely different subject. Namely, I don't want to talk about transition metal oxides today, high TCs or something of these nasty compounds, but a very good old family of heavy fermions, which has become a little bit out of fashion, but still are good in for some surprises. And what I want to show you is not actually material related, which also doesn't really fit into that workshop, but is model related and tells you that also for models where you think you know, or for theories where you think you know, you are in for surprises, especially with your PhD students if they forget to set a parameter to a finite value. Okay, so what is all about? Okay, first of all, the calculations have been done by my PhD student, Oliver Bodensiek, and this was a collaboration with Rok Žitko from Ljubljana. You heard the name already this conference. Robert Peters, who's now a postdoc in Kyoto. Mark Jarrell, who was bugging me constantly about that this can't be. And Matthias Reuter, who was trying to understand why it can be. Of course, money has been provided by Germany. So let's get back to some very, very old stuff. I mean, this ranges from the early 80s till the middle 80s before ITC spoiled the business. We all concentrated on understanding the so-called heavy fermion systems, which are basically built out of cerium intermetallics. So this is, so for example, cerium lead-3, where you see, and I apologize for the bad quality of pictures, but they're taken from Fisher of B papers mostly. Here you see chi, here you see delta T. This is the specific heat as function of temperature squared, in fact. Now, if you look at the values here, you might realize that there is something missing in contrast to your normal metals. Namely, instead of having a millijoule here, you do have a joule here. So these values are of order joule per mole in Kelvin squared, which is huge. Normal metals give you 10 millijoule per mole in Kelvin squared. So it's actually 100 times or even 1,000 times the value of the bare electron systems. That's why these guys are called heavy fermions. At the same time, the susceptibility is enhanced in a appropriate way. And the funny thing is, if you dope this stuff by lanthanum and then scale the curves as a function of by the amount of cerium in the system, you see they all collapse on top of each other. Also resistivity, now this is cerium copper 6, which has become also notorious because of its quantum critical features. If you look at the resistivity, this thing as function of cerium doping goes up as cerium comes into play. The high temperature regime always looks a little bit similar. If you look, this is a logarithmic scale, so there has a logarithmic divergence here, well, logarithmic behavior here, crosses over into something, and down here it's more or less t squared. The surprising thing was that in 1978 or so, Frank Steglich showed that one of these beasts, cerium copper 2 silicon 2, becomes superconducting. Now this is quite interesting because cerium has one F electron, which has a local magnetic moment. You can't actually get rid of this by Jahn-Teller or everything. That's stable by Cramer's rule. So you have magnetic moments in the system. There is a superconductivity, and those don't like each other really very well. But nevertheless, you see this is a bulk effect because the specific heat jump is humongous. And the second thing you note is that it's on the level of this 1 joule. So it's not in the band electrons, it's the whole system. The whole heavy quasiparticles become superconducting. And this triggered more or less a whole industry. Nowadays we know, well, don't ask me how many of these guys which have become superconducting. And presently also, since material design has become much more reliable, we know that these systems are actually much more complicated. They show several phase transitions, magnetic, superconducting, they have quantum criticality, and all these kind of funny things that has become very fashionable over the past 2 decades or so. Okay, so let's wrap up the historical facts on heavy fermions. One finds an extremely large Sommerfeld coefficient constant and a Pauli susceptibility. this stuff scales with the amount of rare earths in the system. The Wilson ratio between those two guys is of the order of 1, say 2 or 3, 4 maybe, which tells you that both enhancements are due to the same physical process, and it's quite likely that you have something like a Fermi liquid around. The low temperature resistivity, unless you're in the quantum critical regime, which I try to avoid today, is proportional to T squared with a prefactor which is proportional to the Sommerfeld coefficient squared. It's called Kadowaki-Woods ratio. And that also tells you that the resistivity is driven by these kind of properties that lead to your enhanced thermodynamics. You find bulk magnetic and supermagnetic order, which is driven by these heavy quasiparticles. And, well, this is more or less uninteresting for the present talk. Now, the standard interpretation is that you have Landau quasiparticles with an enormously enhanced effective mass. And the physics behind this is because you have this intimate connection between the amount of cerium in your system and the properties, is that this is due to the presence of local moment on the F electrons. And I will just name the effect behind that here. It's the Kondo effect, and we will talk about this tomorrow in the school for those who have never heard about that. So just keep in mind, this is some effect that gives you extremely enhanced Fermi liquid properties. We will talk about this tomorrow. Okay, so this was the introduction. Now the model and the method. There are actually two models to describe heavy fermion systems. They are not the Hubbard model for one kind, but they're called periodic Anderson model, which is consists of a set of non-interacting quasiparticle states called D. For whatever reason, you can also call them C or whatever. Then you have a localized electronic degrees of freedom called F, for obvious reasons. If those guys sit on the same side, they don't like each other, and they strongly interact with the U, which is typically for cerium here really large. This is of the order of several 10 EVs. And then, of course, in order to make things interesting, those guys talk to each other, and they do that via hybridization. So that's a standard model. Now, there's one particularly interesting limit, namely, if you put this F level well below the Fermi energy, which is typically the case for cerium, the W-occupied level, which is if you put the second electron in way above the Fermi level, which is also typically true for cerium, and at the same time, restricted charge fluctuations, this is Fermi's golden rule, more or less, N C of 0 is the density of states of the band electrons at the Fermi energy, times the average of this hybridization matrix element, to be small compared to those energy scales. Then one says one is in the so-called Kondo limit. What then happens is that you basically can integrate out the degrees of freedom. I will also talk about this tomorrow in the school, and end up with a localized degree of freedom as spin 1/2 in that case. And the rest of the game, like these local interactions and hybridization, they will lead to a isotropic exchange interaction between this localized spin and the band electron spin, has been shown by Schrieff and Wolf, and thus leads to the so-called periodic Kondo model or Kondo lattice model. KLM, not the Dutch airline, which is given here. So again, this is untouched. The band electrons do not really feel that transformation. And what you're left off with is an additional term which contains a J, and this J is related to a certain combination of U, V, and this epsilon F, times the spin-spin interaction between the localized spin and the spin density of the band electrons at the site of the F electrons. Okay, so if one ignores the origin of the J, one can again distinguish two cases, J less than 0, which means you have ferromagnetic coupling. Then one knows that this stuff shows interesting magnetic properties. It has been studied in the connection with the rare earth pnictides and transition metal oxides. You can imagine the EG T2G splitting leads to localized EG spin, which couples via Hund-through coupling, which is ferromagnetic to the EG electrons. Then you have this kind of model. J less than 0, that's the interesting kind, because that comes out from the Schrieff-Wolf transformation, is antiferromagnetic. So sorry, J bigger than 0, which leads to the famous Kondo effect. Again, advertisement for tomorrow's school. And the so-called local Fermi liquid suggested by Nozière, and that's the basic of the heavy fermion physics. Fine, good. Now, this is all kind of phenomenological. We need to actually solve that, and what one wants to see is the interplay between Kondo effect and maybe magnetism. I don't want to talk about that here. One wants to possibly see quantum criticality. I don't want to talk about that one here. One expects unconventional superconductivity. I want to talk about this part here. with the origin probably spin fluctuation because you have a correlated system. So there's a good chance that standard BCS based on phonons doesn't really work, and in fact the experiments show that the objects, the superconducting order parameters are definitely not S-wave, they're quite likely D-wave of that sort. Now, although this Kondo model looks very simple, I mean, you know, the Hubbard model looks very simple, but it's a beast to treat. It's again an extremely complicated many-body theory, a many-body system, and you need a reasonable approximate solution. Now, I am, of course, one of the protagonists of this type of mean field theory. So what I would like to use first is the dynamical mean field theory for several reasons. There's one price one has to pay. And Antoine will talk about this tomorrow, and you will also learn about this next week. You can take into account only local correlations. There's no way to really study non-local correlation in the sense that two objects at different sites speak to each other dynamically. This also means you don't have any non-local dynamical order parameters. And that's bad, because D-wave is the non-local dynamical order parameter, even if it's static. So the consequence here, at least within this simple approach to dynamical mean field theory, you can study only S-wave superconductivity. If you want to go to higher order angular momentum, P-wave or D-wave, you have to do clusters at minimum. Well, that's too complicated for me, so let's stick here and see what the model can give you regarding S-wave. And as the impurity solver, and again, tomorrow I will talk a little bit about that, I will use Wilson's numerical renormalization group, which is, so to speak, the impurity solver if you only have to consider one electron, one band, spin-dependent band. Good. In order to set the stage, what you can do, or what you have to do in order to study superconductivity is you need to go beyond the simple DMFT, and that can be done very simply because you know that, or maybe you know, that you can describe superconductivity by introducing the number formulation, which means you combine electron-hole pairs into one spinor, and then everything becomes a 2x2 matrix. So everything you know about DMFT, or will learn about DMFT, which contains a sigma, that's usually a scalar, you can also replace that by a 2x2 matrix, and then do the calculation or the derivations using this 2x2 matrix. Just keep a little bit care about ordering of factors. These are nevertheless non-commuting variables anymore. Okay. Good. So that's the quick and dirty introduction, and now let's do some physics. What I want to show you here is basically what heavy fermi physics means from the point of view of models. And I do that by showing you the single particle properties. This is the density of states of the band electrons as function of omega. W is the bandwidth, and I'm using here, I hope you can read this, a two-dimensional square lattice. And I have a band filling, which is not 1, but it's 0.8. Why do I use a two-dimensional square lattice will become clear in a moment. As you know, or well, you should know that mean field theories don't really care for the lattice, for the dimension. So in order to give a good presentation, I can pick the one I think it's most convenient here. It turns out 2D. Okay, let's take a look. I should modify this figure, actually. Let's take a look at the red curve first. This is ferromagnetic J, which I said is interesting for magnetic properties, but not have fermions. And if you look very carefully, you see this typical two-dimensional density of state. This has this Fraunhofer singularity at the Fermi level. You see that here. You see these band edges. Everything is a little bit smeared, but that's about it. So you can, if you look at it with a loving eye, you can recognize the two-dimensional density of states. Now, if you turn to the antiferromagnetic J, where you expect heavy fermions to live, the thing becomes quite dramatically different. It shows this pseudo-gap type of behavior with two separate bands, funnily. And okay, here you still have kind of Fraunhofer singularity, but this is definitely not anymore the bare density of states of a two-dimensional electron system. Now, it's hard to tell from that figure what is going on, and that's why I was using 2D, because what you can do is you can look at the spectral function in the two-dimensional Brillouin zone. Three-dimension becomes a bit more awkward for the next step. And that's a typical square lattice, so you have the square here, then, or actually the half-filled Brillouin zone would be this square embedded here, And typical paths you go through the baryon zone are from gamma to M to X and back to gamma. And that's what's shown here. This is gamma, this is M, this is X, and this is gamma again. And up here, it's again the J less than 0. That's the ferromagnetic, sorry, this is the ferromagnetic down here system. And you see, again, with a loving eye, a very nice cosine tight binding dispersion. But up here, the system has become quite different because now you have actually two bands. Out of one band, you make two bands, which tells you have a doubled number of fermions in your system. One living very close to the Fermi energy, actually becoming very flat here, and that tells you this is this will have a very strong, high effective mass. And this one up here is a bit of a vegetable. And in fact, these are the two objects you see here, and this is basically the broadened single particle band down here. You can even go one step further and ask yourself, what is the momentum distribution? And that's, next thing is you can try to interpret this in a very simplified mean field model. And what you then get is the result that actually the system should show hybridized bands, where from the mean field treatment you now get two degrees of fermionic degrees of freedom. One's called the C particle, that's the conduction electron. And this is basically the one that should go through here and here again. But you see this is split into two parts. And an immediate part where this thing has little weight is now covered by a new one, I call F particle, which is the screen stuff. And that becomes flat at the Fermi energy or close to the Fermi energy. And that's the reason is you have the higher masses. And this is something that's well known for years, this hybridized bands picture. And as I said, what you can then do is you can ask yourself, what is the the momentum distribution, what is the Fermi surface in the system? And that's shown here. And this is what I would like to say is one of the most striking effects of Orlando Fermi liquid theory. Namely, down here it's again J bigger than 0, so less than 0, there's a ferromagnetic coupling. And what you see is basically we have 0.8 electrons in the band system. So what you see is there's this black line sitting inside the half-filling square, which is what you expect for such a system. And okay, it goes down. It's not really a step function here, but this is due to the broadening effects we've in our system. System becomes quite different if you go to the antiferromagnetic heavy fermion material, because then you see there's nothing actually at the 0.8 part. On the other hand, you have a very nice jump here at 1.8. So you have surprisingly one electron more in the system, or one fermion more in the system than before, initially. And the jump is not 1 anymore, but it's smaller. That tells you two things. First of all, we have a Fermi liquid. This Fermi liquid contains 1.8 fermionic degrees of freedom. I wouldn't call them electrons. This is dangerous. The electrons are this. And there are 0.8 electron systems. But here you have a Fermi liquid, which contains 1.8 fermionic degrees of freedom in the system, with a Fermi surface out here. And the effective mass of these objects is extremely enhanced because the jump is a measure for the Fermi inverse mass has become quite small. That's heavy fermion physics. This is a large Fermi surface you expect in heavy fermion systems, and that's how it comes about from the model. Again, these are not electrons. These are just counting fermionic degrees of freedom. And I will talk about this tomorrow again regarding the Kondo effect. Okay, so I have to hurry up a little bit. Superconductivity, the thing we started was, well, we don't expect D-wave or any funny superconductivity in DMFT because everything is local. So in order to force superconductivity, let's add phonons. They do that. Since we can't do any better with our method, let's add Einstein phonons with a Holstein coupling. And what you know is at J equals 0, if you put this guy away, you get conventional S-wave superconductivity or charge ordering, depending a little bit on the system. If you have ferromagnetic coupling, we don't know. That's something we would like to do at some point. It might be interesting because then you have ferromagnetism competing with superconductivity, which could lead to P-wave or whatever. No, hard to get. The J bigger than 0 is the interesting one, and there you expect an interplay between Kondo effect, which is a spin-driven effect, superconductivity and charge ordering, which are charge-driven effects, and they do not like each other, so you expect a competition. Okay, so doing the calculation, what you find is shown here. That is at T equals 0, half filling, some value of J, which is not too small or not too large, some value of the phonon frequency, which is not too small because you have to be careful, otherwise your cutoff procedure in the numerics becomes a little bit questionable. What you find here as a function of electron-phonon coupling is that at large electron-phonon coupling you have a wonderful superconductor and the local moment of your spins is just 1/4. So there's local moment living separately from the superconductor, and that's about it. That's what we expected, and then at some point there was a drop, which does not go to zero, not fully go to zero, it becomes very small. At the same time, the local moment drops. So that means that although Kondo and charge do not like each other, they, under pressure, cooperate and form a heavy Fermi liquid which becomes superconducting by the phonons. This was kind of surprising, but not really outrageous, so that's okay. And then one can go on with the calculations and ask you. Now, this was the state of the art 2 years ago, and I taught my student to go on. And this could be, in principle, all, but it isn't. Namely, what he did is to start serious calculations, but unfortunately put G equals 0 all the way. And what he ended up with is this result. So this is now the Kondo lattice model without phonons. Okay? DMFT Kondo lattice model without phonons. And you find a very nice superconductor. Very stable, nice superconductor. What you see here is the density of states again as function of frequency. Shown in black is the solution with a finite superconducting solution. Plus the red dashed curve is the paramagnetic solution. Now, that this is really superconducting shows the right-hand panel, because what we show here is actually the ratio between anomalous self-energy, that's the Nambu part which does not, is not diagonal, divided by the Z factor, if you like, and that is finite. That if that object is finite, you get everything you want, namely Meissner effect, supercurrents, and so on. So that tells you that this is really a superconductor and not some kind of fancy insulator appearing here. And you see another thing, namely here is an additional structure, and this additional structure that actually lives on the scale of J and moves out if you increase J. Likewise, those objects here in the gap. And the size of the gap, namely at the value of 0, is increasing as you increase J. So there seems to be a clear connection between the J and the superconductivity. Now you can map up the whole phase diagram. What I show you here is what we call the order parameter, which is simply the anomalous expectation value C up, C down, as function of filling, and J at T equals 0, and always G equals 0. So there's no other glue than what the system can provide itself. And you see there's a wonderful stable island, a rather large one in fact, of superconducting solution to the model, except for half filling, where you don't find anything. Well, there's a very small island, but we're not sure that's true. And at very large filling and very large J. You can also ask yourself how do these things look along certain cuts. For example, at a fixed filling, 0.9 as function of J, you go through a maximum, and actually this maximum appears somewhere where the Kondo scale, which is T0 half, becomes, well, not maximal, but rises strongest, and then goes down again in a region where the Fermi liquid scale or the Kondo scale more or less saturates. And the same is more or less true at function of filling for a fixed J. More interestingly, if you now look again at the spectral function, okay, hurry up, you see that you find these kind of Borg-Lyubov quasiparticles here, but if you look very closely, there's another stuff happening out here, namely additional structures in the spectral function which go beyond these Borg-Lyubov quasiparticles. And what you can then do is again do this mean field analysis that gave you the hybridized bands picture, but now add these superconducting correlations. That's the main field Hamiltonian here. I don't solve that self-consistently. I just take results from the calculation, put it in for the effective parameters here, and then see what comes out. And that's what comes out. But you have to be careful. Namely, what's very important is you have to actually use these off-diagonal CF pairing amplitudes. The other ones do not do that much. So those are the important ones, and they give you precisely these structures, Bourdieu quasi-particles, plus these additional crossings here at higher energies, which you observe also in the calculation. Also, that's final temperature. So how much time do I have? Two more minutes? Okay. So to wrap it up, we do get, obviously, superconductivity. The only thing that can drive it are spin fluctuations. There's one problem with spin fluctuations. They are usually considered to be repulsive due to the funny algebra of the spin operators. There are several approximations involved in these kind of arguments, and so one can ask which one is the relevant one here, and one could be that you usually say epsilon f is much larger than any fluctuation scale, so use a static approximation. It turns out that, in fact, let me go through that in a hurry, is that this is not really sufficient. So you can actually do the calculation using a dynamical kernel here, which in that case would be the spin fluctuation, fluctuation rate, chi double prime. It still doesn't really give you the right sign. And if you then say, okay, now let's take Fermi-liquid theory, that is, put all the self-energies to 0 more or less. They have very small omega variation, as Antoine told us, but this is not important here. Nothing happens. Now here comes into play the funny structure of the heavy fermions, because there the self-energy is actually not 0, but it's that structure here. It's v squared effectivization divided by omega plus or minus some kind of shift. These are the hybridized bands I've shown you in the beginning. And if you insert that self-energy into the calculation and actually assume that all omegas of v squared, mu, the spin fluctuation scale, you need the dynamics then, are of the same order of magnitude, namely of the order of tk, which is the Kondo scale of the system, then indeed you find a very nice and extended island of attractive interaction from these spin fluctuations. So there is an interplay between different effects here, namely, first of all, that everything is driven by Kondo fluctuations, which gives you a local energy scale that governs everything. And second, that you have the hybridized bands, that is these additional fermionic degrees of freedom, and what you get is an intra-band superconductor here. And, okay, that's all. Thank you.
Thank you. Yeah. We have time for some questions.
So if you happen to open up a D-wave channel in this case, will your S-wave superconductor still survive, or it's just an artifact?
Very good question. Actually, André Tremblay might still remember Benjamin Lenz. He's still here? Oh, yeah, okay. You may remember Benjamin Lenz. He stayed with you and for quite a while. He's supposed to do these calculations using a variation cluster approach. It turns out that, in fact, the Kondo model, doing ED for the Kondo model is a pain. Okay, forget the second word. But he's now able to do that. And so what we want to do is using the variation cluster approximation for the two-dimensional Kondo lattice to see whether we can find a D-wave solution, and also see whether this type of solution actually appears anywhere in the parameter space, or actually whether you have a D plus IS or anything of that sort. Yes, so it's on the way, but it's quite dramatic, because doing cluster calculations for the Kondo model, like CDMFT, is really, really expensive.
Yeah, just a clarification. So if you take the TJ model, for example, you get an SI.Sj, and that you can actually
once again, if I take
in the TJ model.
Yeah.
So you get a JSI.Sj, and then you can actually sort of look at it in the pairing channel. Right?
Yep.
So isn't that a similar thing that's happening, that you get this JSF.Sc, and then you're pairing, you're looking at it in the pairing channel, and that's what is driving superconductivity?
No, not really. The TJ model has been studied in the connection of high TC superconductivity. Now the big difference here is that the TJ model doesn't drive your heavy Fermi behavior. It gives you a correlated metal. But this is not quite heavy Fermi, because heavy Fermions, as I said, you need these hybridized bands, and that's what not appears within the TJ model. So the spin fluctuations there cannot profit from this type of interband scattering.
Yeah, but the glue that is giving you the superconductivity.
That would be non-local, so that would rather drive D wave. Here we have a purely local glue. Yeah. That's also another difference.
Nice.
No, but I think it is very similar.
It's very similar.
You have two entities,
right,
Yep.
So your interaction is non-local because C and F are not in the same place. They're not the same orbital.
Yeah. Okay, good. Yeah. Okay, good.
Right.
I agree. Right.
Yeah, that's exactly the point.
Yeah, in fact, I had the same question than these guys. So basically, the statement that spin fluctuations are repulsive I think, does not really apply in the antiferromagnetic Kondo case. You have a decoupling, right, in the C dagger I up, F dagger I down channel, which I think is indeed attractive in the case of antiferromagnetic Kondo. At half filling, as you showed, there is no superconductivity because there is an exact SU2 rotation, and there is no distinction between C dagger, F dagger, and C dagger F. Both phenomena describe the Kondo effect. But away from half filling, these channels are distinct. I think that's what's going on.
Oh, I completely agree. The big point is, for example, if you live with Mark Gerald, well, I don't live with him, but if you
that's an interesting revelation.
if you work with him, the immediate question will be that in normal systems, the spin fluctuations are repulsive. So you need to have the non-locality to have this change of sign in the gap function, then it works. And this is not possible here. You have a frequency dependence of the gap function, but that doesn't change sign on the proper scale. So you need something else. That was the idea why we went through this kind of...
Actually, I had another question, which is that you made a very interesting observation about how well does Eliashberg, Eliashberg for spin channel, does in comparison to the actual DMFT solution. And this has an important aspect, which is the importance of vertex corrections and whether the mean field... Okay, so can you comment more on the actual punchline on that?
You mean that figure here?
Well, I mean, does Eliashberg, does a simple...
This is just a qualitative argument why where this becomes attractive. I don't say there's a TC or...
But did you try to make a comparison with integral equations that you would get by some simple Eliashberg
No,
treatment?
the big problem is I don't know these prefactors properly, so I have to make assumption about the prefactors. You could try, in fact, yes. I mean, that's something one could try. One could actually use the self-energies you get from You could use the self-energies you get from the DMFT calculation, plug it in here. No, I haven't done that. That's a good question. But I remember that actually Jim Freaks, did this for the Anderson-Holstein model, and a Hubbard-Holstein model a while ago, and found out that it's not Eliashberg is good at low frequencies, but it turns pretty fast, pretty bad actually.
Yeah, hi. So my question is regarding there are some works in the literature where they start from the valency fluctuations and basically understand this unconventional superconductivity in heavy fermion systems.
Well, once again.
So there's an alternative mechanism of starting with the valency fluctuations. So I'm referring to the works of Miyake, etc. Yeah. So I'm curious, how is that for the unconventional superconductivity, you have two alternative mechanisms of spin fluctuations and then valency fluctuations as well?
I don't have any valence fluctuations.
No, here we don't have, but they start with valency fluctuations.
Very, very good question. Now I have to make a confession. The big problem is I would love to study the Anderson model, where you have both objects. There's one problem with the numerical renormalization group and Anderson model. They don't like each other. So doing DMFT for the Anderson model with NRG is almost impossible. So you have to resort to other techniques, and that's what we're trying to do right now. It's just a matter of number of students you have.
Yeah. A very simple question. Can you go back to your phase diagram with the Holstein coupling and the J?
Oops. I'm sorry. This was yes. I can do that.
That was an easy question to answer.
No, that's fine. Yes.
Okay. Now, where? So this phase diagram. I'm just trying to understand how this relates to the superconductivity at G equals 0. If I put your G equals 0 points on this phase diagram, where are they? What's going on?
This is half filling.
Ah.
I see. This is half filling.
So if I were to draw a diagram away from half filling, how would it look?
Well, sorry, that's
with G and
that's something we did not yet finish because the problem is my student stopped working before he could finish that part, but at least there are some preliminary results on the influence of G. And what you see here is that quite interestingly, as you start from, this was 0.9, so this is where the maximum basically is. If you increase G, then everything goes down quite nicely together. So there's one big question. If you increase G further, you might, you actually expect that at some point BCS, let's call it that way, takes over. And then the question is, does it go all the way to 0? Or does it make a dip and come up again? This would correspond to what we've seen, that you have a heavy fermion phonon-driven superconductor. And I guess that's the second what you would see. The question is how far below that goes, I don't yet know.
I see. So therefore, you're really saying that this G equals 0 superconductivity is really a new phenomenon.
It's a new phenomenon.
Because the phonons are bad for it. Right.
Yeah.
Thank you.
Yeah, I think we are running late, and we'll close the session here. Let me again thank both the speakers of the session for wonderful talk, and also all of you for participation, and thank the organizers for again inviting me to chair the session.